And here I have some more practical examples to show you the application of compound requirements in the case of object-oriented programming. Consider this implementation of shapes as a hypothetical third-party library. The implementer of the library provided an abstract class shape and an implementation class called square, which publicly derives from shape. The base class or the abstract class provides two pure virtual functions, namely print and draw, in its interface, and the derived class correctly overrides these two methods. If you notice that the print method in the implementation and the base classes are private and is used only for overriding the std_o_stream operator, which is provided as a friend function in the base class only, and it correctly delegates the call to the print method in the derived class through the virtual table, since the friend function accepts the second argument as a reference to the base class. Now there arises a situation that the client needs an extension of the library since it doesn't provide all the shapes. Say library client wants to implement more shapes like rectangle and circle. And since the private methods are not visible to the client, they know nothing about the existence of a private print method in the library components. All they know that the shape has a public method draw and can work with stdcout to output some details on the console. In this situation, the client decides not to inherit from the base class of the shape. Therefore, the client provides the shape with just these two methods. And one of the client or the user wrote some utility functions and decided to make it generic, so that it not only works with the library components but also the extensions of the library components. Say for example, the utility functions are drawShape, that simply calls the draw method on the shape object that it receives as an argument, and printShape, which streams the shape argument received in the function with stdcout. Now a second client comes along and provides a shape rectangle, but in this case forgets to provide the public method to make it streamable with stdcout, but it works with the utility function drawShape since it provides in its public interface the method draw correctly. Therefore, the drawShape can call on rectangle the method draw, and we get the functionality of the draw from rectangle as expected. And a third client or the user of the library now comes along and provides the circle class, but misses out on providing the public method draw, but ensures that the class works fine with stdcout by providing an overloaded operator that works with std_o_stream. In this case, the method printShape works fine since the class provides std_o_stream operator as a friend function, but it doesn't work with the drawShape. Now, another user might try to use this. For example, they instantiate rectangle and try to call the drawShape, which will work fine because it provides the draw method. But as soon as they try to print it with the utility provided by the library, it won't work. Similarly, in the case of circle, the printShape will work, but the drawShape will not work. And we get an error again in this case. Let me comment out these two calls for the time being. Okay, now let's discuss how we can fix these issues in the utility functions so that the library authors or the client who are shipping their own library, they can prevent such issues. In C++20, they can provide a constraint on the template parameter shape type such that the constraint ensures all the interfaces on the shape are provided correctly. Let's call this constraint shape interface. Let me type this out here. Let me use this as a named concept. Concept shape interface equals to requires keyword. You all know how to do this by now. Shape type shape. In the body of the constraint, I have to check two requirements, namely shape provides the public method draw, which returns a void, and the expression stdcout streamed with shape is well formed. So let me go ahead and do this as a compound requirement. The first one is shape.draw, and it should return std same as, if you remember, we have to use a standard concept or any concept, but in this case I'm using the standard concept std same as. void. And the second requirement is the expression std cout with shape should be well formed, and it should return std convertible to std o stream ampersand. Now I can use this requirement here in the draw shape and print shape. So I can use it as a trailing requirement just to show you a variation. Requires shape interface with the template parameter. I can simply copy this here and apply this on the second generic function. Now our two utility functions are completely constrained. If I go back to the calls and try to call the print shape on rectangle, we will get a much readable compilation error. Let me clear the console first. And here we go. The compilation error, first of all, is very small. And the error reads as in the draw shape, when called with rectangle, the required expression is invalid because the expression std cout with shape is not well formed. Similarly, if I comment this out and uncomment circle, I get an error that the shape.draw expression is not well formed. Let's go ahead and fix the errors now. So here I just need to provide an overloaded OStream operator, which is a friend for the rectangle class. I can simply copy this and paste it here. Get rid of the comment. Yeah, and here I replace circle with rectangle. Similarly, in circle, I have to provide a public draw method. Now, if I go back to my main file and comment everything, clear the console, and try to run it once more, everything works fine. Now we can play around with the concepts a bit more. For example, if I change this to int, everything will stop working because the draw methods in the shape classes return void. Let me show you by compiling and running the code. Here we get the error from each of the calls, namely the expressions are not well formed because they don't return int. If I change all the draw methods to return int draw cost, clear the console once more. So now all the draw methods are returning an int instead of void. Although I don't provide a return statement, this is a warning, but still it will compile and run. And finally, I wanted to show you the second variation in the compound requirements, namely compound requirements can also be used to check if the expression is non-throwing. For example, if we take all these requirements, we can impose a restriction that these expressions don't throw by applying no except keyword after the curly braces but before the arrow function, like this. We can do this also in our current example. So now let me revert back the int to void. And now I can impose the requirement that draw should be no except simply by typing no except. And now if I compile and run the program, I will get a compilation error, namely the requirements on draw is not satisfied because draw method is not no except. Now I can make it no except by simply adding the no except keyword. So now all the draw methods have no except. Let me clear the console once more. and it works again. We can also add no except here. This implies that the friend functions is also no except. Here also no except. Also on the base class it should be no except. Alright, that's all I wanted to show you in this lecture. So stay tuned and enjoy learning modern C++. Thank you. Hello there. If you enjoyed watching this video, don't forget to hit the like button and subscribe to my YouTube channel. If you have any questions or if you would like to start a discussion on the topic covered in this lecture, please feel free to leave a comment on this video. And lastly, if you are interested to learn more about my courses, then log on to my course website mastering-modern-cpp-features.thinkific.com. Thank you.